We are system architects in Oberthur Technologies in Łódź. And we would like to talk about non-blocking approach for building microservices in Java. So firstly, what we are doing in Oberthur, to just give a context. So Oberthur is focused on security, and everything, each project and product of Oberthur is around security, mainly about customer needs around connectivity, authentication, and payment. What Oberthur is doing, the core business, is secure elements. So credit cards, like you can see here, we have some example credit cards that are produced and personalized by Oberthur.
Fancy ones.
Even some fancy ones. This one is, you can see inside the NFC antenna. We have some aroma card that you can scrub and feel that it's a flavor of coffee, and some others. So in those credit cards, there are chips, and those are so-called, in general, secure elements. And this is the core business of Oberthur. What is more, when you have a SIM card, this is a SIM card, but in regular one, in envelope, SIM card is as well a secure element. And in fact, it's exactly the same technology, SIM card and credit card. And those secure elements are produced by Oberthur. This is the core business. And those are actually computers. There is a chip with operating system inside, with JVM. Yeah, I was surprised when I joined Oberthur that inside credit card there is JVM, and I can upload their Java application. Those applications on those chips are called applets. This has nothing to do with the web application applets. Maybe the older from you remember the Java applets in web technologies.
And it's not the regular Java at all. It's some restricted kind of flavor of Java, so it's not.
Yeah, but still Java. Yeah, and so those secure elements are chips that are aligned with the so-called Java smart card specification. So those are Java smart cards with operating system and JVM. And what is more, especially in credit cards and SIM cards, those are secure elements. So the word secure is important. Those devices are tamper resistant. So theoretically, we are not able to hack it. Well, there are no things. Yes, there are no things in the world that are not able to hack, but it's really expensive and hard to hack those devices. We can store data there in secure way. So we can store cryptographic keys inside credit card or SIM card or another flavors of secure elements, and you can store it in a secure way, and hackers cannot get out those secure keys from inside. So this is the core business, and I already mentioned that we can have Java applets there, Java applications inside, and we can manage that. And this is what we are doing here in our office in Łódź. We are working on a server-side systems that are sometimes deployed in our secure cloud in Oberthur, not in Łódź, but somewhere around the world in a few data centers. Or sometimes those products are deployed on customer premises, in banks or in telco operators, and so on. And what we are doing in those server-side systems, we are managing what's uploaded to those secure elements. So we have a bunch of secure elements on the market, in your phones. By the way, Oberthur is the second biggest supplier of SIM cards and credit cards. So probably half of you have in the pocket Oberthur product as a SIM card, as a credit card, or even if you have a Samsung Galaxy, inside you have embedded secure element in each Samsung Galaxy starting from S5 or S4. There is inside the secure element from Oberthur. So this is the context of what we are doing.
And yeah, and to technical part, actually, what is demand?
Is this keynote presentation available for downloading?
Not yet.
It will be. Yeah, we're gonna present it at JDD conference in 2 weeks, and after that it will be available in the internet.
Yeah.
On SlideShare probably.
So let's switch a little bit to technical part. So what demand of the market actually? So as Michał describes, our our servers like performing in some crowded environment, and the clients of it actually it's MNO or banks. MNO the mobile network operator, like Plus, Orange, and all the stuff, or banks. And from the other side, our clients are actually those secure elements which connected to us and trying to acquire some keys, some data, personalization, and all this stuff. So those devices actually, as you can understand, they're small and they're slow. So they're maintaining a lot of long-running concurrent connections to it, to our servers.
By the way, sorry for interrupting, on such a chip, there is up to 33 megahertz processor and up to 4 kilobytes RAM memory and 156 read-only memory.
So, and as soon as we are performing in such big crowd environment, we also need to be scalable and resilient, so this leads us to this known microservices architecture.
Doesn't work.
No? Okay. So what actually microservices perform in the regular IT system? They actually perform acting like gateways, yeah. So they are receiving some requests, like making requests to other services or databases or something like this, accumulating the data, like synchronizing to accumulate all those data, somehow processing it and responding or not to the client. And actually those operations in general are IO intensive rather than CPU intensive. And the most intensive CPU intensive part is Marshall and go request. So nothing special. And in our domain it's also, but our domain also contains those secure part, which are actually
it's about cryptography.
Cryptography, yeah. And this is like additional servers, and we are not actually implementing them, we are working with them.
So we have some such use case that we would like to present you. We built a demo based on this use case that I will present in a moment. This use case will present actually it simplifies scenario what we are working on a daily basis together with Alex, Gosia, Julia, and a few more people here.
If you sure can disclose the real code what we have.
Yeah, but on
security.
On the GitHub there is this demo, simplified scenario, which based on this use case we try to test blocking and non-blocking approach, how it works. But first we need to introduce the use case functionally. So in this secure elements business domain, usually, like I said, there are some secure elements inside phones, different devices inside the cars. By the way, Mercedes-Daimler, the new Mercedes-Daimler, they have embedded secure elements from Oberthur to have ability to have secure communication with the server side. And there are some server-side services, usually so-called TSM, Trusted Service Manager. This is the class of the systems that would like to manage what is uploaded to the secure element, do it in a secure way, and everything is around security, so that's why it's called Trusted Service Manager. As it is about security, so in general, in high level, it looks like that inside those secure elements, there are stored in a secure way cryptographic keys. And to communicate with them, all messages that we send to them need to be deciphered in a way that they can decrypt them with those keys. To cipher it, we need to have a key on the server side. And as everything is about security, it should be stored in a secure way. So usually you have a system called hardware security, HSM, hardware security module, which is again hardware module. The keys can be stored inside in a secure way. There is no easy way to hack it and get those keys out from this device. And what is more, as those secure elements of the market in cars, phones, there is a lot of them, millions. And we need to have a key to pair with them. If we know that I would like to send something to Alex's SIM card in his phone, I need to cipher it in a way that only his key in his SIM card can decrypt it. So I need to use HSM. And of course, we do not store in HSM all the keys for all produced secure elements. We have a master key. So actually, few of them. But we have a master key in a secure module. From the master key, there is algorithm to diversify the key that match to the particular secure element. And with this diversified key, we can secure communication. So we have a separate module which is called, usually it's hardware security module, actually always. But in our case, this is just a demo presentation. We will have a software mock of this. And the process inside, in the central place of this process, there is OTA gateway. OTA stands for over the air. So if there is over the air communication, usually with SIM cards, in general with the secure elements that are embedded in devices that have connectivity. So for example, if secure element is embedded in the car, usually the car have GSM module and can communicate with the outside world. If we have SIM cards in a phone, it has connectivity, and so on and so on. So we have OTA gateway that orchestrates this process. So we have a DSM that can manage, if there is a database here, and someone here can manage, administrator, what should be uploaded to particular secure elements. And to provide the connectivity, we use the OTA gateway. And this is actually the piece that we are working together on a daily basis at Oberthur. So the process, how it's used, it looks like that firstly, the TSM want to submit some scripts. This is a specific terminology. The messages that are sent to the secure elements, they are so-called scripts. Actually, this is a list of the commands that need to be executed on the secure element chip. So they are so-called scripts. And in a single request, we can send multiple of them. So first, the TSM submits script, and then we need to encrypt those scripts, because here they were not encrypted, they're just free-form scripts. We need to, on the server side, encrypt them with the secure key stored in the hardware security module. And this encryption is time-consuming, as this is cryptography, algorithm, and so on. So a lot of CPU-intensive calculations. Then such a script we store in a database. Usually it's no SQL database because we need a lot of throughput and low latency. Yep. Then when we stored it successfully in a database, in a kind of a buffer, we respond to the TSM, okay, those scripts are accepted, encrypted correctly, and we are sending them to the secure element. Because secure elements are inside devices that we don't know IP address or another address for connectivity, usually those devices need to poll for those scripts. So such a device can ask, do you have something for me? So devices came to another HTTP endpoint and asks, give me scripts for me. Then we can read those scripts from DB. Search for a script for particular secure element based on some ID, and give back the script to the secure element in device. So in general, the architecture looks like that.
And of course, aside of that, we have some supplementary systems like a monitoring system, log storage. So it's a lot of endpoints and a lot of like IO path in the system.
Yes, and what we would like to show is that when we are thinking about non-blocking application that is using non-blocking IO, we need to think about all IO in our system. So we need to think of all edges actually of our application. So here we have an HTTP endpoint for TSM. We have communication as a client with security module, HTTP endpoints for secure elements, some connectivity block storage, and gathering monitoring metrics via another HTTP endpoint. So we have a bunch of the I/O places. Those are all places where I/O in our application is performed.
So, what actually drawbacks of no blocking, of classic blocking I/O? Yeah, you are forced to have one thread per connection. Yeah, those threads actually waiting for some external computation or some external data to synchronize and to produce some result. This leads to big amount of context switches and all this stuff because we have a lot of connections and just not that good. And also that leads to resource wasting because threads are not like free. They occupy memory, they occupy resources and all this stuff. And for example, you don't have something like 4,000 threads on this particular Mac, just OM and that's it. You're crashed. So.
So this is the technologies, how we did our sample. It is available on the GitHub in a blocking way. So we used those technologies to do the blocking implementation. As a database, we are using Redis, in a more efficient database, no SQL. For the HTTP endpoint exposed by our OTA gateway, so endpoint for TSM, an endpoint for secure elements. We are using REST services based on JAX-RS, implemented in REST Easy on top of Jetty. With the communication with the security module on top, we are a client as an OTA gateway. We are again using JAX-RS client on top of REST Easy that is using underneath the Apache HTTP client. For logging, we are using Logbet and logging just to this. Yeah, the SDL. For connectivity with Redis, we are using Redis, which is I think most popular Java client for Redis, and it's the blocking one. The
recommended one on the site.
So those are the technologies that we use in the blocking version. We are using Jetty here. As probably some of you may know, Jetty under hood is non-blocking. And yet that's true, but for our example it doesn't matter so much because we are using this Jetty in a blocking way. So we are processing, we are invoked in some thread by Jetty, and we are doing all processing in this thread. So we are blocking this thread for the whole processing. Yeah, and we implemented this example and we should test it. But firstly, before we test OTA gateway, we should test our secure module mock. So the security module mock, usually in normal life is hardware, but here it's just a mock. It's implemented in Java 8. It emulates latency. Each request to encrypt something to this module emulates latency 200 milliseconds. So I'm sending it a request, please cipher it for me, and I'm getting response in 200 milliseconds. Okay, this is encrypted message. Firstly, I thought, okay, let's test, do the performance test of the whole system. But firstly, I thought, maybe I should firstly test the security module if it works well under even huge load and do not change my results of the whole system. So firstly, I tested the security module. For testing, as a load generator, we used Gatling, which is quite nice tool for doing performance tests. It's written in Scala.
Yeah, and actually the main benefit for us is just Gatling creating a lot of concurrent real connections and not reusing it. So for us it's really like the case.
Yeah, I was doing those tests on my laptop with Windows on 4 cores CPU, actually 8 virtual threads, 16 GB RAM, but it doesn't matter for Java. and load generator both. Load generator and tested system were on the same machine. This is how you shouldn't do performance tests. This is against any rules.
Yeah.
But for me it was okay, because what I actually wanted to test is not the performance of the whole system, including networking, how networking performs and so on. I just wanted to test if my components perform well, without the overhead of the networking outside of the machine. So I decided to do the tests, to do the load generator and tested system, to put it on the single machine. Yeah. And those are results. I expected some problems, and there were no problems with the security module mob. So we'll have such a diagrams a few more times for different test results. So let me explain what you can see. On top, this green part is number of responses per second. And on the very top, you can see 100 requests per second, 1K requests per second, and so on. This is our test scenario, how many requests we send. So first, for 10 seconds, I sent 100 requests per second, and the system was performing well. Then 1,000, then 5,000 requests per second, still performing well. And then 10,000 requests per second, we can see that the responses, number of responses is not 10,000, like I'm stressing the system, but it's about 7,500. And we can see this orange line is the number of active, it's called on the right, you can see number of active users. This is because Gatling is operating on terms of like a users, but actually this is number of requests on a load generator that are awaiting of response.
Actually, number of connections to the
yeah, number of connections that are waiting for a response from the tested system. So we can see that this simple mode can perform well up to 7,500 requests per second, which is quite a lot. So this is how to read the top diagram. And the bottom one is the latency. Because it doesn't make sense to measure only throughput, which is a request per second. You always need to measure throughput and latency and present both. Because only then it makes sense. What does it make sense to have throughput, I don't know, 1 million per second, while latency is really, really, really huge. So we need to take a look at latency. And latency is how long it took to get a response. And we can see here that I said on a previous slide that I'm emulating 200 millisecond latency. And you can see here, 200 milliseconds. All requests, and even in my testing, it's much more than it can receive. So I'm sending 10,000 requests per second, while it can respond only 7,000 requests per second. Even then, latency is around 200 milliseconds. So it's really stable, and always, no matter how I stress it, it always responds in 200 milliseconds. So it's a good mode. And those colors that you can see here, and those are percentiles. You can see it on the right. So the green one is minimum, and the red one is maximum, and for example this one is 99 percentile. So it means that this color, it is somewhere here, for example. It means that 99% of requests ended in latency better than presented here. So here is around 200 and I don't know, 210, 220. So 99% of requests ended faster than 220. Alright, this is how to read those.
The maximum was 229.
Yeah, here you can see maximum 229, which is quite good. We stressed more than it can process, but latency was still very good.
In real world, HSMs not behaving like this. So
it's really opposite in the real hardware security models, because there's cryptography.
So we're using clusters of that.
We are only emulating this latency. So how we achieved the latency over 7,000 requests per second on a simple laptop. And this is the code. It's Java 8. What you can see here, it's a REST service, JAX REST. What you can see here is that it's already not blocking. So we have this suspended. We are not blocking thread delay 200 milliseconds. We are just getting the async response handler. We are scheduling on a scheduled executor service, scheduled to resume request and respond with the response in 200 milliseconds. And you can see to do that I should parameterize it. And it works. I was surprised that it worked so well in the first try. First of all, why? Because we used already non-blocking I/O. And second, I was surprised that scheduled executor service is really well performing. We are scheduling 10,000 requests for 200 milliseconds delay, and it works well. It gives us responses exactly after 200 milliseconds. Yeah, so now let's talk about our blocking OTA gateway. Yeah, it's blocking, so it behaves like that. Okay? So this is our test, the system that we tested. So as you already know, at the security module mode, we are emulating 200 milliseconds latency. And it's more or less like hardware security modules work. Because in real life, there is no delay or executor service, there is a huge cryptography processing. And on the performance tests, we are emulating this TSM. We do not have a real TSM, we just have a tapping load generator scripts. We are sending in a single request 2 scripts. So in a single request here, we have 2 scripts. Each of those scripts needs to be encrypted in a security module. So we have a latency 200 milliseconds and another script 200 milliseconds. And then it's stored in database, in Redis. Redis is really, really fast, so we don't care so much. We will see it in the result. And we expect the latency of this request would be below 450, probably, because we 2 times are doing 200 milliseconds delay. And this is the first test without any configuration. I just put the load on a just developed component. And it occurred that when I have a load 2 requests per second, it's okay. 5 requests per second is okay. But 10 requests per second is too much for it. And I thought, something went wrong. 10 requests per second is not a lot. No. Come back. And what we can see here, not go too fast, when we are sending 5 requests per second, we have 5, more or less 5 responses. 5 responses per second. And when we send more, the waiting connections are, the orange line is growing. And you can see latency is growing. And this growing, the latency here is more than 10 seconds. We expected 450 milliseconds, but it's 10 seconds. Well, really bad. And so then we analyzed what's going on, and it occurs that we are using as a client of the security module, we are using, as I presented, REST Easy JAX REST client, and underneath it's using Apache Commons HTTP client, which by default uses 2 connections per endpoint. Because this is how it is stated in HTTP standard. In HTTP standard,
everybody breaking it, but it's still like that.
Yeah, standard says, please be polite, do not open more than 2 parallel connections as a client to the same server endpoint. Nobody do it. In browsers is usually 5 to 10 parallel connections, but we need much more. And it makes sense. Why it was so slow? We have 200 milliseconds latency, 2 scripts in each request. So it seems that we should have 4 requests per second, 4 or 5 requests per second here. This is exactly what we achieved. So we reconfigure it. And to have 200 connections available on HTTP client. And for Jetty here, we didn't reconfigure it. By default, 200 threads on a Jetty when you do not configure it. And we run tests. And it looks like that. For 100 requests per second, it performs okay. For 200 as well. For 500 requests per second, we can see that orange line is growing. Not fast, so probably we are just a little bit above the acceptable limit. And latency is growing as well. So, okay, so we achieved more or less probably around 400 requests per second. Not bad, but we tried if we can better. And we reconfigured those connections and pull maximum 1,000 connections and maximum 1,000 threads on a Jetty pool that is accepting the processing the requests from the client. And it looks like that. But for 500, it's okay. No surprise. For 1,000, okay. And for 1,500, we can see that latency looks more or less okay, but we can see that this orange line is starting to grow a little bit, so it's a little bit too much for that setup. So we can say that we achieved a little bit less than 1,500.
Roughly, it equals to the number of threads serving those requests. Roughly.
Yeah, it was configured 1,000 threads and 1,000 connections, and a little bit above 1,000 requests per second it can achieve. We can take a look at the resource consumption. So, as expected, we configured maximum 1,000 threads, and threads we can see it's 1,000. Heap memory, it consumed above 1 gigabyte of the memory. And we can see the response, actually,
rate of responses and
process rate is interesting here. So we can see that in a moment it was around 1 and 1.5K, 1,500 process per second.
Okay. So let's switch from blocking to non-blocking. So yeah, actually we have the same setup, but we are a little bit changing the technologies we are using there. And here we need to show different slides. Actually, here we're switching the technologies, and here we're using async HTTP client for the query actually security model, and nothing else. Just yeah. Little bit changes the driver to the DB to the non-blocking one, and the technology under the serving HTTP request stays the same. It's still Jetty, so nothing more. And yeah, we run it and receive it something like this. Oh. So it's without any additional configuration, something like this. We even not increase it, but decrease the number of serving threads from 1,000 to 16. It actually can be less because it depends on the number of processors you really have. And we receive such results right from the start. Like we have this 2.5K requests per second without real degradation. And if you look at the latency, it's quite good. So under more or less under what we're actually expecting, like 500, something like this.
And what's interesting, if we stress non-blocking solution more than it can process, so this 3,000 requests per second, we can see that the orange line, the connections waiting for response are growing, number of connections, but overall latency is not growing so much. So it's still stable. Even if we put the more that the solution can process, the latency is still good.
And how it looks like internally. So we have a number of threads. Actually, we have 2 endpoints configured on the 16th thread, plus some executor on the Redis driver and all stuff. So roughly it's 55 or 57 threads was consumed. Also, memory consumption was pretty low, like 477 megabytes, and everything else like more or less stable. Like the curve of the request, more or less the same, like curve of responses. So latency, as we said, the same, so no degradation.
Okay, and when we compare those two results, we can see that to process, this is on the left is blocking approach, on the right non-blocking. The blocking approach can process maximum around 1,200 requests per second on the same machine, while non-blocking twice as much. The blocking is consuming more than twice more memory at 1,000 threads, while non-blocking it uses only around 50 threads. But this is about resource consumption, but what is more significant, at the top you can see a screenshot from the Gatling report, this load stress tool, and you can see the latency. So even if we stressed with 2,500 requests per second, the non-blocking latency was really good. The maximum was 561. We expected around 550, so it's a little bit more than we set up the limit, but a little bit. For a blocking approach, even 75%. So it's 2.5 seconds. So really bad. Even 50% is around 800 milliseconds. So we can see that half of the requests ended with the latency around worse than 800 milliseconds. So it's not good.
Yeah. And if you enable debug logging, so it's good. Yeah. Oops. Debug logging. Yeah. So this is actually a detailed slide on the technology that I already mentioned. So we use it like a async HTTP client without any configuration at all. We use it like REST-easy with Jetty and JAX-RS 2.0, the suspended annotation, just to start execution in a synchronous way. We use it like this really cool driver, non-blocking driver Lettuce, based on the netty. Async HTTP client also based on the netty. And yeah, and switch it to async appender for the logback. So just to not block like execution.
So actually to do it right, when you are thinking about non-blocking processing, you need to think about all edges of your application. So all endpoints, as a client, as a server, you need to think about having it non-blocking, because if one of the endpoints is blocking, then especially when you are a client, probably you are blocking some thread that is from the non-blocking pool, and you shouldn't do it. And another thing about technologies, previously as a client of security module, we used JAX-RS client. And when we switched to non-blocking, we tried to do it with JAX-RS, but it's not possible. JAX-RS client is, I think, not well specified. Each implementation acts differently. REST-easy
is awful in terms of it's not thread safe at all. So as soon as we start, you need to create a lot of clients, and it consumes a lot of memory.
Yeah, it's stated in spec that I don't remember if the client itself or the client factory is not thread safe. So we need to, each time we need to create a new one, and it's stated also in the same Java doc that it's time consuming. So we have to switch to the HTTP client, which is just a native HTTP client. It's not JAX-RS anymore, it's just HTTP client with the netty underhood.
So no fancy HTTP formatting.
No annotations, you need to serialize by yourself JSON and send via HTTP.
Yeah?
So non-blocking looks great according to the results that we presented. And let's focus how it was implemented. So this is the blocking approach. And this is our scenario on a sequence diagram. So we get a request from TSM to OTA gateway with scripts, in our case 2 scripts. Firstly, we are logging it. So we have blocking IO to log something. And when we are waiting until it was logged and written to the file, we are waiting, the first red part, we are waiting and wasting time and resources. Then we are sending requests to encrypt the script. And during the encryption, what our thread is doing, it's blocked. It's blocking IO. Our thread is blocked. So the second red block, we are waiting and wasting resources. The same with storing in database and doing all that stuff. doing the communication with security module is the largest part, because this is how it's reality. We are using Redis, so DB is really fast, but hardware security modules are really slow because they are doing cryptography, extensive CPU computations. So we are wasting here, the red parts are the parts where we are wasting our resources in our application. We have blocked threads that they exist, but they are doing nothing, and it's consuming memory and so on. So when we switch to non-blocking approach, it looks like that. We are not wasting, I just removed those red parts, and from the helicopter view, it looks like that we are sending a request, doing something else. We are not wasting, we are not actively wasting resources. When the response comes, we got a trigger and do some more processing, and it looks very nice, and that's beautiful. But in fact, in reality,
devil in details.
In reality, it looks like that. And that's even not true. It looks much worse, but actually this is all asynchronous processing, and sequence diagram do not fit into presenting asynchronous process as well. So let's try to describe it. There comes a request to the HTTP server. The thread from the HTTP server pool goes this request to process it. It's doing some logging, but the logging is now non-blocking. So actually it's sending an event to the logging thread pool. Hey, when you will have time, please log it. And then it's sending, we don't know if logging already occurred or not. It's a different queue and thread pool. And then we have the second line, request to the security client, please encrypt it. And that's it. But we don't know when it will be encrypted. We are waiting. Then the logging was done, then the encryption was done, and when we have encryption response, the response is achieved by the thread from the security client thread pool. And then the further processing is done on the security client thread pool. So the request to store something in database is to form the model, the entity with Hibernate, or however we are using database. We are using Redis, so no Hibernate. But all the processing is done in security client thread pool. Strange. And then we are asking DB client, please store it in database. And again, we don't know when it will be stored, here or maybe somewhere else. I don't know even how to present it on a sequence diagram. Then we got the response and the same. We are logging the response, and we want to store something else in database, so we are submitting task to the DB client thread pool to do some other DB operations. And it looks on a diagram really messy. And in fact, it's just a simplified version. In reality, it's much, much more complex. And this is the main problem with non-blocking approach, that it's really hard. It's really well performing, but it's really for hard.
Yeah. And actually, we wanted to show the code probably in details, how it looks blocking, unblocking. Blocking that I think you all of you are familiar with. Yeah, it's hard. So yeah, this is actually how it looks like blocking version. Yeah, we have the submit scripts method. We little bit instrumented it with this metrics. It's Java 8 feature. After that, just to trace our business flow, we just put in something to MDC just to be able to understand from logs what's happening in our system, where we for which secure element we are receiving request and all the stuff. Making some debugging logging, processing some scripts. It's good. Debug, asking secure module client to encrypt scripts for us, one and after that second. Making some stuff. Actually storing script into the database, and everything looks good. Retrieving a number of strings from the database, actually counted it, and returning back the result. Very, very easy, very fancy, and very understandable.
This is standard blocking code, and any Java developer can read it and understand what's ongoing. We are doing this, then we are doing this, and then we are doing that, and we can read it. If we have, good names of the methods, we can understand what's ongoing.
And we are switching to the Non-blockable.
Yeah.
Yeah. So it's non-blockable. How it looks like? We also instrumenting with some metrics, but instrumenting stage. If somebody interested, I will describe it a little bit later. So we have this. Actually, we are performing on completable features like the latest feature in the Java. So we are using completable features to actually create this asynchronous logic to sequence operations like in non-blocking way. So we started with some completion stage. We performing like first operations, just asking asking secure model to encrypt those bits, but actually to not duplicate code, we force it to create additional function, just a little bit more. So we have this one like secure module encrypt, then compose, processing some requests. After that, actually, we need to call Redis to store that script. It's some kind of spaghetti already. So we are then composing with this completion stage and returning the result of those. Like actually, we build in those completion stage, a sequence of them. So returning back to the. So yeah, and we are processing it like in the loop. But as you see, we need to make some tricks just to stack them, stack all those operations, and using those really not that safe operations like this stage null, not using final properties, final fields, and all this stuff. So and after that, we need to complete, subscribe for completion stage, and actually resolve the async response is actually the promise. In this case, to resume it with an exception, or resume it with a real result of operation. So code looks not that straightforward like it looks like in blocking way at all.
The main problem is that in a blocking scenario, we are doing things one by one. Do this, I have a result, then with the result do this, that, and so on. It's linear. And here, when we are submitting something to be processed asynchronously, we don't have a result in hand. We just have
only promise of it.
We have a promise, which is a completion stage, CompletableFuture underneath, and we can only chain those futures. That okay, please do that, and when you will do that will be done, please do that, and when that will be done, please additionally do that and that and then, and complete when and complete then, and a lot of hard stuff that is really hard to write in a readable form. This is the main issue. It's really hard to understand what this code is doing, and when you are doing non-blocking application, you need to do it in whole application, because all edges of your application should be non-blocking. So all code of your application should be aware of this asynchronous processing, and it's really tough to do it in a readable way.
I wanted to also highlight some like very important for us aspects like tracing our flows. Yeah. So in this case, we need to trace somehow like and bind the real log records to the real like flow which we are performing. Like in blocking way, you can rely somehow on the name of thread or something like this, and after that trace the logs under which thread it was executed, how it was sequenced, and all this stuff. When you're performing it in non-blocking way, a lot of thread executors, you have no such clue. So you need to add additional information every time. The very obvious solution, you like use MDC, but MDC also not working in this way, because MDC is using thread locals, and there is no thread locals when you pass in between different threads. So you need somehow pass this like diagnostic context. We are using for it in this case some immutable object like login context. Very simple, just two final fields in it, like the name of the flow and the ID of the secure element. And we need the way to actually pass it to each stage of the computation, like this. Here we are using actually closing, because this is like function, yeah, this is closes on this logic context, but we need to pass it inside that additional function to be able to log with this logic context. So yeah, it's not that. And if you have more complex sequence of the actions, it becomes a real nightmare. So something like this. Okay, I already mentioned it while I'm describing. So it's hard to those are drawbacks. It's really hard to debug because you have no clear surfaces. Each time it's executed on different threads and all that stuff. So you really more rely on logs and on the debug logs and trace the flows because of what I have mentioned.
Okay, the challenges of introducing non-blocking processing in a standard Java application, Java Enterprise or whatever, is that, for example, the servlet API, initially it was thought and designed as a blocking API, and the non-blocking approach, asynchronous, was introduced in servlet spec 3.0. The same with JAX-RS spec. It was introduced the non-blocking approach in JAX-RS 2.0. And you can do it in an asynchronous way, which we proved because our application is using REST-easy JAX-RS implementation and it performs well. But there are some drawbacks. For example, some decorators like filters and so on, they are still designed in JAX-RS spec as a blocking. So we cannot use those fancy features of JAX-RS, of chaining, aspect-oriented programming and so on, because this is meant to be blocking. Latest Java containers, in general web containers, under the hood are designed as a non-blocking, and they are using non-blocking I/O, like Jetty, for example. But a lot of code libraries that we are deploying on top of it, that we are using in our applications, all of that is designed with the standard blocking approach, and sometimes we cannot use some libraries because it doesn't fit our asynchronous non-blocking processing, and there are a lot of such cases. And the most important, the readability. In general, in Java 8, there was introduced those CompletableFutures, and this is what unblocked the ability to chain those computations like we did. It's still not really super readable, but we can do it in a standard way. There is CompletableFuture in Java. In previous Java versions, there was nothing standard. So there was some Guava futures, Netty futures, they have their own. Redis client, Lettuce, they have their own futures. Everyone was doing it on their own way. So that's good that Java 8 standardized it with the CompletableFuture. About technologies, so when you are doing REST services, RESTful web services, you can use JAX-RS 2.0, in general 2.x. Like, for example, we used REST Easy, and it works fine, except that those decorators filters are not working. Netty is a great library, great stuff.
Actually, in our project we are using it extensively. We are using it on both sides, and we are actually not using Jet in our projects. We use a Netty-based under the hood executor of the REST Easy. So we are actually Netty. We have Netty everywhere on all the endpoints, client servers, and everywhere. And
even if we are using Lettuce, which is a client library for a Redis, non-blocking, Lettuce under hood is using Netty. Netty is really good non-blocking stuff for Java. So if you are considering to write some non-blocking code and implement some protocol, even so, I would recommend to go Netty because it is really good stuff. Another framework for non-blocking is Akka.
Yeah, it's Akka, and latest version of it have this I/O, HTTP, reactive streams part, so you really can implement everything in a non-blocking way, plus actor system, under the hood, so they are non-blocking by nature. But sorry, it's better use it with Scala, Java. Our guys actually tried to use it in Java, but readability and issue they face it, it's like
the Scala developer is promoting Scala everywhere.
Yeah. Sorry for that.
So that's about servers, and for clients, if it's HTTP, we definitely recommend using HTTP client 2.0. Usually in our applications we have some databases or other kind of storage, sometimes SQL, sometimes NoSQL. So for NoSQL databases, the modern one, usually there are some non-blocking clients, like Let's for Redis, there is something for Cassandra, for MongoDB. Most of those modern NoSQL databases, they have non-blocking clients because those databases, NoSQL, they are meant for a high throughput, low latency. So usually the non-blocking approach comes good with this. If we have SQL database, there is bad news. JDBC drivers are blocking by its nature. The API is designed that it's blocking, and we cannot use it. For some SQL databases, there are non-blocking clients. Yeah. For example, for MariaDB, the MySQL clone, there is non-blocking client. It's not JDBC. It's a really different API. But if you want to use MySQL or MariaDB actually in a non-blocking way, you can use it by some proprietary API.
Yeah. Okay. So probably let's continue on what we have learned when we implemented all this stuff. For us, actually, JDK 8 is plus some libraries like Netty. It's enough to build microservices and in non-blocking way. Actually, we don't need any additional monstrous frameworks like probably Spring and something like this. Async code really can be readable, but you need to adapt to it somehow and probably apply some functional patterns because without it, it's really hard to build all those sequences of the operation that you need to perform. So as soon as you are using several threads, you really require some immutable data structures. In Java by default there is no such things. You can implement something like this, but something like with final fields and all this stuff. But you don't have. You need to create a lot of code. We have found solution. It's some kind of it's called immutables library, which actually generates on the compilation stage of Java immutable objects with all fancy getters. It's actually not getters, but with methods, which actually transforms objects from one immutable stage to next immutable stage. So, but it's required, and we are also right now looking into this JavaSlam library, which implementing some Scala libraries on top of Java 8, something like this. Unit tests. Yeah, as we fought a lot with unit testing because asynchronous code, as you may understand, really hard to test as soon as we have a lot of threads and all this stuff. So for us, the rule of thumb, they should be synchronous. So you need to test it in synchronous way, probably restricting the number of threads in the thread pool. Sometimes you need to create some kind of additional develop your own tools just to make the scenario of the test looking like scenario and not like a lot of asynchronous code under the hood, because you need to support those tests later on. And if you implement it really hard to it by other people, it will not go anywhere. So this is like some kind of change. And what's really fun?
Yeah. When you are developing the non-blocking system for a good throughput and low latency, you really need to test it and stress your system, because there are a lot of places that you can tune and you can do things wrong. You can forget easily that you used some blocking library or you did some blocking operation, and then the performance of the whole system that can degrade. So you really need to test it. MDC, already mentioned by Alex. MDC for contextual logging is based on a bit of the thread locals. So we cannot use it in a non-blocking asynchronous processing. You should name your threads properly. It really helps, especially in our case when we have Netty everywhere. On all edges of application, we have Netty, and if with the default configuration, we have everything which is ongoing, it's in Netty thread. So you need to really name those thread pools separately to know what's
according to the subsystem in your system. just to understand where this rooted actually, where this operation was rooted.
Yeah, because we have a lot of those non-blocking subsystems, we should plan for how to configure them. In each of the subsystem, client of external system exposing endpoint, we have some thread pools underneath, so we should plan it and plan how we will configure and how we will test configuration, that is right configuration, how huge thread pools we need on each of those endpoints. You need to be prepared for some non-obvious errors, like we did from REST Easy, with the out of memory, from direct memory buffers, from virtual. It was really strange, and mainly because of the asynchronous processing. When you have asynchronous processing, you may have some leaks and problems with managing of the resources between different threads.
Enough heap memory, so it's really hard to actually to debug. There's no non-heap. Because heap memory is all okay, but when it becomes non-heap, things are really scary.
Graceful shutdown is also challenging. If you would like to implement graceful shutdown in your application, to shut down gracefully, to close, wait for awaiting connections, resources, free those resources, it's really hard to do it in a asynchronous way. And already mentioned Netty, we really recommend Netty as the tool for non-blocking, doing low-level non-blocking I/O in Java.
Yeah. And the last thing, probably the technically Scala still provides more tools and like creates more readable code than Java 8, unfortunately. So something like this. And final conclusion. Non-blocking computer processing can really save you resources, great money. But weigh all pros and cons and use non-blocking if you really need it.
We do not recommend using non-blocking for a standard enterprise Java applications, because then those applications are doing a lot, maybe not CPU intensive workflows, but they have a lot of orchestration logic and there is a business process inside. And it's really hard to implement this business process in a readable way in an asynchronous processing. But if you are implementing gateways like we are doing, so systems that are not doing much CPU intensive, but just proxying some things and orchestrating and they're really lightweight, then non-blocking probably is for you because you can then do it in an effective way to not waste resources. Yes, and we are hiring at Oberthur R&D Poland in Łódź. We are looking for architects, developers, QA engineers, and integrators. We are using those technologies, as you can see. The Netty that we are talking about is here as well, the Java 8, and a bunch of other fancy modern technologies.
Like Docker, actually, if you look at the source code on GitHub, it's fully Dockerized, so you can actually run your all those examples via Docker Compose. So it's like that.
Yep. And a few stats about our company. So the R&D department is around 700 people all around the world. In Łódź, it's around 150. It's about more than 15 multidisciplinary teams, so we are focused on building products. The same product is deployed into multiple customers, and we have teams that are coupled with that product. The team is multidisciplinary, so architects, developers, QAs, integrators, all are the full-time members of the team. Some other technical stats on our test environments, only test environments, we have more than 500 VMs, more than 2,000 Docker containers running simultaneously, more than 500 Git repositories, and a lot of really funny stuff. Yeah. So thank you. Our demo is available on GitHub. You can take a look. If you have any questions, you can just ask. You can ask in Polish. We understand both Polish.
Yeah. Ask in Polish. If the question for me, I will respond in English.
To ja miałem kilka pytań. Pierwsze jest takie, nocy, uważacie, czy jest sens, żeby pozostały do nie logujące?
Przykładem jest logowanie. Jest sens, tak. Odpowiedź krótka jest tak, jest sens. Or maybe I should respond in English. So the question was, if we want to have non-blocking system and we have a single endpoint that is blocking, is it worth to do somehow work around to do everything non-blocking? And my response is that yes, you can do it. And a good example is logging. We are using logback for logging, and we are logging to the file, actually to the std out, but it doesn't matter. We are just logging to some descriptor, and this is blocking. We cannot write to the same file or descriptor for multiple threads simultaneously, because it will break this descriptor. So this is blocking. Logging to the file is blocking. But we can separate it, and we are using in logback async appender. So whole system is non-blocking. We are using async appender, so logs are just submitted to be logged. And underneath, behind this queue of log system, there is single blocking thread that is writing to the file. And yes, you can achieve the non-blocking system with some blocking parts.
Yeah, the same actually you can achieve if you really have some database connection with DBC driver that you can read of it. So you need to work around it. So main computation will be non-blocking, and this particular part connecting to the database will be blocking. It's okay.
Okay, but how would you propose this? Would it be for this DBC driver? We are going to input some queue or some messaging system?
Yeah, something like queue.
Some queue or some submitting in Java 8. You can CompletableFuture submit something to process, and underneath it will be queued on some thread pool queue.
Yeah, because it has this pool of connection and all this stuff, so it will process it on a proper connections.
Okay. So another question about this different topic, so about Scala.
Okay.
Are you going to rewrite this in Scala? Are you going to rewrite this in Scala in Java?
Actually, no. We have huge database, and actually, what we have shown, it's like the top of the iceberg. Under the hood, we have a lot of really standard-specific stuff, and it is complex stuff. It's cryptography, some protocols, and all this stuff. It's really, really hard to rewrite. So we need to use already written code, and really, it's time-consuming to rewrite it. So we are using like regular Java implementations and using this non-blocking I/O to make the conversation with services.
Yeah, but you could also rewrite only the gateway. You could rewrite only the gateway.
In the gateway as well.
Gateway is not on the gateway; it's quite complex.
Yeah, it's quite complex under the hood. So it's a lot of.
It was just a simplified use case.
Yeah.
Yeah.
What tools do you use for performance tests?
Gatling. We are using Gatling, which is a tool written in Scala. You write test scenarios in DSL language. I don't know Scala, I can write only hello world, but I can write scenarios in Gatling, and it's really good tool because the good thing is that this tool is non-blocking itself. So when you tell to this tool, please load this application with 10,000 requests per second, he's trying to do it. And there is no, if application has some latency, it's not responding fast. For example, in JMeter will not stress this application because JMeter is blocking, has thread pool, and if you do not have enough threads in the thread pool, those threads are waiting until the previous response will be responded and then send the next request. So if you tell, you cannot tell JMeter, please stress it 10,000 requests per second no matter what. In Gatling you can do it. It's not fully non-blocking, so we can stress the application how you want. There is no sprzężenie zwrotne. But there is no back pressure and relation between tested system and load generator.
But Gatling still have this drawback, like JMeter. Yeah, JMeter can be like orchestrated by multiple instances, and like JMeter will like orchestrate all those instances of load generators. Gatling doesn't support it, so you have like single instance on single machine. So to actually bootstrap huge load on different machines, you need to like invent something your own actually. Actually, we are planning doing something like this because we have complex web services and microservices. So we actually using Gatling like a scenario runner, which actually after that will orchestrate load generators to generate load from both sides of the system just to stress it, something like this, and on different machines, of course.
And on the other hand, to run it on a single machine, with Maven you can do it easily. It's really easy to run it. There was a question somewhere there? No? Okay, so thank you very much.
Yeah, thanks a lot.
And I think there is a moment for lottery.